Our next presentation is on software-defined radio and amateur radio. That should be interesting. Hopefully we're going to learn how to redo our own radios. That would be neat. So we can pull the manufacturers. Lyle Pic A 7P is the presenter. And I'll have to let you give us some of your background because I don't know it. So I'll turn it over to Lyle. Can everybody hear me okay? Loud and distorted? Okay. Well, my name is Lyle. A little background about the APRS talks this morning was using something called packet radio. I was one of the founders of Tucson Amateur Packet Radio back in 1981 in Tucson. In those days, my car was WA7 GXC. Moved to the Northwest about 7 years ago. Love it up here. I'm sick and tired of all that sunshine down there. I don't worry about sunshine up here at all. I'm going to be talking about several areas of software-defined radio. It's a huge topic, and it's one that could go for a long time, but I'm going to spare you for that. We'll try and zero in on it. One thing that we oftentimes run into a problem with is time for questions at the end. So does anybody have any questions at this time? Okay, all the questions are answered. We'll go on with the presentation. I'm not too good at using these wireless things, so I'll probably just do this and see if it plays. Okay, what is software-defined radio? Always when you're talking about something, it helps to define terms so everybody knows what you think you're talking about so they can catch you in an error and point it out during the question and answer period later. For our purposes, a software-defined radio is a radio whose primary functions are defined by software. This isn't computer control like you've got an old AC something, rather an old Kenwood 850 or something that has a jack on the back so you can use a logging program to control it. That's the software-controlled radio, but it's not the software-defined radio. For software-defined radio, you really need to be using something we call digital signal processing. And that's simply a method by which the signal is digitized and then everything is handled in digital after that. So software then runs the digital signal processing algorithms to do things like create demodulators, create data decoders, and code things, send out an APRS packet, whatever it might happen to be. And the software that tells that digital signal processor how to work is in the software that, generally speaking, defines the radio. Some radios, Tentec has been an early adopter of this kind of technology. Since about 1999 or 98, with the introduction of the Pegasus, you could actually update the software on the radio. Now, I have to shift gears here a little bit. Part of my background is with ANSAT, where we create satellites and launch them. And people got really excited when we started launching the microsats because some of us that were responsible for the design and operation of the spacecraft took the advantage of the fact that the spacecraft were now software defined so that we could kind of sleep at the switch a little bit and not really get the thing done before it was launched, figuring that we could catch up after launch. Not a good idea. No, I understand the difference between kilometers and miles when I go to Mars. Not related to NASA. Now, most brands of radios don't allow you to update the software that's in the radio, even though they are software defined. For example, I have an Icon 746 Pro at home, and it's digital signal processor based and all the rest of it. But if the software needs to be changed, that's too bad. Now, a lot of us are getting really interested in software-defined radio and amateur radio because with the advent of the internet, there's been a kind of a decline in some of the excitement about talking to somebody that you don't know. You can do that in the chat rooms and so forth. But the idea of experimentation and self-education, being able to get your hands around it, as parts have gotten smaller and smaller and harder to solder, it's nice to be able to get into things and be able to manipulate them in the old experimental kind of way. And software-defined radios allow us to do that. The talk just before lunch was showing the use of software applications to expand the usefulness and functionality of an APRS network, for example. There's all sorts of open source examples of software-defined radio. Without going into a lot of detail, you can read the slides. WinRAD and DSP, things, Power SDR, are tremendous examples of software that you can get the source code, you can look at it, and in no time at all you'll either be asleep or confused. There's other software that's available, but not open source for various reasons. I'm sure nobody here ever heard of non-open source software, so we won't get into that. The little graphic on the top is showing you a little bit about with the software-defined radio. You really need very little hardware. Antenna signal going into a bandpass filter. You go into what we call a complex mixer. That's just to confuse you. It really means there's two of them. And then you filter the information, you digitize it, and off you go. And for some software-defined radios, this ADD part is a sound card in your computer. So all you need is this stuff, which is much more complicated than a crystal set. And I'll show you some examples of that a bit later. Sir? Complete with a cat whisper, yes. And if you can find the chunks of Galena, then we're all set. Okay, here's some examples of software-defined radio that came from the ranks of amateur radio. In September of '99, QST came out with an article by somebody in the Northwest, Bob Larkin, W7POA, and he made a little 2-meter transceiver that was software-defined. It was a 3-part series in QST, and a lot of us got excited and started buying parts to build some of these things, and TAPR kitted a couple, 300-400 of them. And it was using a little evaluation board you can buy from analog devices for the digital signal processing part of it, and a little DOS application program that Bob wrote on his computer so he could do weak signal 2-meter work. And you could do AM, FM, sideband, CW, all sorts of weak signal move bounce modes and all the rest of it. And the software is free, it's downloadable from his website, and it's kind of a fun project. It's also mentioned in a book called Experimental Methods in RF Design. For anybody that's an experimenter, you have to have a copy of this book. It's kind of like a magic decoder ring. That's what the book looks like. I don't work at the ARRL, but if you don't have that book, get one. If you get one, read it. And if you read it and understand it, you'll probably get a pay raise. The first commercial software-defined radio, apart from the Tentec Pegasus, was Flex Radio's SDR 1000, which was introduced in 2003. The first time I saw one was at the Dayton Convention in May of '03. And I didn't really want to spend $500 for a stack of 3 little circuit boards, so I hemmed and hawed and waited about 3 months, and then I spent $500 for a stack of 3 little circuit boards. Gerald Youngblood wrote an excellent series of articles introducing these concepts that were published in QEX, and they're now available for download from the ARRL site, even if you're not a member, or you can go to the Flex Radio site and download them as well from there. They were printed in QEX, which again is QEX. If you're a member of the ARRL, you need to get QEX. If you're not a member of the ARRL, you need to get QEX. Gerald wrote the original code for this using Visual Basic and a free library that Intel was making available in those days. Since then, the community, because it was open source, has written software that's just light years beyond what that original stuff is. And that's been done largely by Bob McGuire and Frank Brickle. And it's a little interesting there because Bob works for a company that works for a 3-letter agency of the government, and they thought that this was an interesting technology, so Bob was able to get his employer to get funding from you-know-where, so that Bob could, on company time, be developing all of this SDR stuff, because it is applicability to what they're doing, but because it's open source, of course, we all get the benefit of it as well. And so basically, Flex Radio gets to leverage 2 brilliant people and doesn't have to pay them a dime. For that, I don't understand why the radio costs $1,500, but somebody at Flex can explain that, I'm sure. A couple of more examples of software-defined radios. Some people thought that that was a lot of money to spend, and they were right. So a guy named Tony Parks got all involved in wanting people to get involved in software-defined radio at a low price. This looks similar to that. This is one of Tony's little radios. This particular one never made it to market. If that's hard to see, I can lower it and make it a little harder. I'm sorry that it's so small and it has to be the physical size thing. But this plugs into a USB port. This has a sound card built into it, this particular one. So all you need is a USB port and a 40-meter antenna, and you can look at about a 100 kilohertz swath of 40 meters, all modes, not a problem. The ones that he has made available more generally don't have the built-in sound card, so you've got to have one. And he also made a transceiver This is how far I've gotten in building my transceiver kit. But Doug here did get one built. So this is like a $40 kit, and it's all mode, and is it 1 or 2 bands, Doug? It's a 2-band radio, about a half a watt to 1 watt output. Again, all bands, all modes. It's about $40, right? 35, okay. Plus, give Tony an extra 5 because he's selling him 2 sheets, so it's 45. Excellent product to sort of get your feet wet in this without spending a lot of money. It's even cheaper than some of those APRS things that people were talking about earlier. Hendrix has a little thing he calls a Firefly that was designed by Dan Taylor. It's a kind of a hybrid, therefore it costs more. But on the other hand, it doesn't work quite as well. Then there's a company called RF Space in Georgia. This is a couple of hands. Peter and Mo, and this thing basically takes HF in. It's got an ADD converter running at 65 megahertz. That means it can go from DC to 10 meters without a pause, and has a USB port, plugs into your radio, and boom, you get a panoramic spectrum analyzer kind of display of what's going on. Click on a signal, listen to it. It's also a very good spectrum analyzer tool. It's a lot of fun. I got mine for less than that price as listed there. I got serial number 1 of it. I was very fortunate to get that. They've come out with a lower cost, smaller version of a similar product that they call the SDR IQ that they're just now bringing out. These are, in my mind, they're very interesting things. But they're just examples of software-defined radio. Inside the box, you can see that there's not much there. That whole thing I held up earlier, there's not much there. Moving the functionality into the software. Now, the Pic A Star project is one that I find very interesting as well, from Peter G3 XJP. I've got to show you his call sign right. It's based on an embedded 16-bit digital signal processor chip, and he took the code that Bob Larkin wrote and modified it a lot and expanded it and turned it into stuff that worked really good in the HF context. And one of the guys that was an early adopter and a beta tester of this thing was Harold Johnson, no relation, although a couple years ago we claimed I was his twin brother. Harold's about 82 years old. Anyway, Harold was one of the guys that was involved in the Signal One project many years ago that you may remember, which was the ultimate radio of its time. Harold's a very confident RF guy. He says this is the best radio he's ever used. Coming from Harold, that's quite a thing. There's a Yahoo group you can go to get more information. But to give you an idea of the hardware that's being replaced by the software, this is a block diagram of the DSP code that's running inside of the radio. Now, if you use the block diagrams, you'd look at that and you wouldn't know that it was software or hardware, because you see mixers and filters and noise blankers and squelch gates and modulators and all the rest. That's just all lines of code that are running inside the digital signal processor chip. Well, that's nice that you can buy a radio from Flex, that you can buy some of these kits and whatnot. But it turned out that some of the people that bought the Flex radio product in late 05, about November maybe of 05, they started thinking about it would be fun to play with field programmable gate arrays, an FPGA. It's basically a chip. In the old days, I don't think anybody here is as old as I am, but when I was a kid, I used to buy parts and solder them together and make stuff out of them. It's harder to do that now because I can't see the parts so well. And solder has lead in it and so forth. So the bottom line is an FPGA is just a whole big junk box full of all sorts of digital logic that you can wire together by typing in a keyboard instead of using a soldering iron. Anyway, these guys wanted to invest with field programmable gate arrays. They found a little board called a Xylo board from a website called FPGA for fun. And some guys bought this thing and said, hey, this is cool, can we do it? So there were some discussions about, well, gee, wouldn't it be nice to build a better sound card? One of the problems that you find with some classes of software-defined radios is that they do use a computer sound card. Those computer sound cards aren't designed to be the front end of a radio. So you wind up with poor sensitivity, you wind up with spurious responses, you wind up hearing signals where there aren't any, or seeing signals that aren't there. It's kind of like a digital mushroom, I guess. So that one didn't very well, wrong practice. Yeah, there you go. There you go. So anyway, what happened was these guys started getting together. There was no organization, there was no group, there was no dictator, just some people getting together and saying, hey, we should do something with these things. Let's go somewhere with this. And so a little group was called, formed called themselves HPSDR. Unlike some people who said it doesn't mean high-priced software-defined radio. It's intended to mean high-performance software-defined radio. And this is, it's a collaborative effort. It's basically spontaneous in nature and international in scope. We have participants from Europe, from Australia, even from America, just all sorts of places where you would expect this sort of thing. All the design work that's being done in HPSDR is open source. All the software and FPGA code is. Some people were a little nervous about making the hardware designs open source in the same sense that software is. It's a little harder to get your hands around it. Fortunately, or unfortunately, a previous president of TAPR, John Ackman, NAUR, happens to be an intellectual property lawyer. So he donated his time, and several of us provided a lot of input, including Bruce Perrins, if any of you in the software or the open source realm and understand who Bruce is. And John created a thing that he calls a TAPR open hardware license and a slightly different one called the TAPR non-commercial hardware license. And the idea is that we can create hardware designs, put them out, people can use them, and just like with open source software, we can make improvements and feed it back to the community, the hardware can have its improvements fed back to the community as well. The TAPR Open Hardware License, or OHL, is currently, it's on the TAPR website at www.tapr.org/OHL, and is open for public comment until March 7th, so we can get some ideas about what we're doing wrong and how to make it better. So, okay, that's enough about the background. So what are we really talking about here? This is a block diagram from the website, which is hpsdr.org, and there's a wiki page from there that you can go to as well that has a lot of the very most up-to-date information. But this is a block diagram of some things. This is a thing, I'm sure you can read. Anybody in the back not able to read that? Okay, you all have sharp eyes. Near the front, that doesn't happen. Okay, so this is what we're calling the Sasquatch board, which is basically an embedded DSP, so you don't need to use a PC. This is the thing called Mercury, which is like an SDR 14, only better, faster, smaller, cheaper. This is the Ozymandias board, or Ozy. I'll talk a bit about that, which is a USB interface. And this is Janus, which is a high-performance 4-channel sound card replacement, if you will, but it is designed to be part of the radio. And it all plugs into a thing here with this backplane that we call Atlas. And I'll talk a little bit more about this, but one of the initial applications, because a lot of these guys came from the Flex Radio users group, if you will, was how to make a really good sound card replacement to get the maximum performance we could out of the architecture of that particular radio, which also applies to that little SoftRock 40 module that I showed you a few minutes ago, without having to deal with, this sound card plugs into a PCI bus, but my laptop doesn't really have a PCI bus, and, I got this USB sound card, but it doesn't work so well. So we were trying to find a way to have a single USB pipe to control the SDR 1000 and to provide a basis from which we could do a lot more experimentation and development. Okay. So initially we've got a high-performance sound card for what we call quadrature sampling detector or quadrature sampling exciter. That was that little block diagram in the very first slide. If you close your eyes, you can visualize it again because I'm sure you all memorized it at that point. This is what's used in the SDR 1000, the SoftRock, the Firefly, and the detector that you want to homebrew. These things really are simple devices. They can become complex, but they can sure start out simple. And mentioning adding features like the SDR 14, that's the Mercury board, and I'll talk a little bit about that as we move into the specifics of it. Okay, I already got ahead of myself and talked about the open source hardware and the TAPR open hardware license. So we'll skip right past that. And that's also mentioning that you can make comments about it. So how does one go about designing a product in this kind of an environment? You've got to have somebody leading a project. Well, the way you do it is you get on the reflector of hpsdr.org and just sort of follow things around to see how to do that. And you look around and you see, gee, nobody's making what I'm interested in. Well, so you raise your hand and say, I'd like to make a name of thing that you're interested in. And then you have to go to some kind of a mythology book or Dr. Seuss and come up with a name for your project. That's very important. And if you can come up with a name for the project, then you can become a project leader. Okay. So when you get to be called a project leader or the designer, then you throw it out and the community discusses it. Basically, they say, bad idea. Okay? Then the designer designs it anyway. Then people start reviewing the design. And you wait and it's a deathly hush. You don't hear much. You evaluate this deathly hush. People start making a lot of comments, and you decide, I've heard enough. And at that point, you go ahead and you implement. So it was interesting to me that when some of these designs were talked about, remember we're talking about software-defined radio. The first thing we had to have for our software-defined radio was a hardware backplane, so you could plug the cards in that you're going to be using for the project. This was the first thing that was that, and apart from the fact that it's hardware and therefore it really gets done, can anybody think about why this was done first for a software-defined radio project? Yeah, that was a comment about RF pads, but the real answer is there's no software. There's not a processor on this thing. My jokes aren't going over very well at all. Okay. So this was the first module. We had something to plug things in, so there was discussion of a passive backplane. How are you going to plug these modules together? What are you going to make it do? Pin and socket, card edges, and all the rest of it. Decided to go pin and socket. And then there were the first two pieces we needed for this thing. Phil Covington in Ohio came up with this thing we called Ozymandias. Ozzy was a king that liked to be in control. And this is what an Ozzy board looks like. And it's basically a USB interface and a big FPGA and then some stuff around it. So this becomes, if a person wants to play with field programmable gate arrays, this is a great card to do it with. The stuff that's being developed for it, the software is all open source, it's all posted, the link to it is all up on the wiki at hpsdr.org. It's not all that expensive, and the tools to use it to do all this FPGA design are free. In this particular case, the FPGA is made by Altera. So you go to altera.com and you go to the, I want to download your free software, and then you go have a cup of coffee, even if you do have a broadband link. And a few hundred megabytes later, why does this sound familiar? You have the code, and you fire it up, and now you can go ahead and design your FPGA. And you can design it by drawing schematics, if any of you remember how to do that. Or you can type in stuff they call VHDL and Verilog for those of you that use the different half of your brain. I tend to be to draw the pictures type myself. So this has a USB 2.0 interface. It runs at about 35 megabytes per second across the link, so we can dump a lot of data across there. For example, let's say you want to look at a 10 megahertz swath of band, and you want to get 16 bits of resolution, and you want to get 10 million samples a second, well, you can do that. It's loosely based on the Xylo board that I mentioned earlier, and as said, Phil, NFBD is a designer of that. Okay? But then there's Janus. You like that in both ways. You want to go analog to digital and digital to analog. So the Janus board is one that has a very high performance A to D converter on it. This is what it looks like in real life. Very high performance 24-bit A to D converter. Don't believe all 24 bits on any 24-bit A to D converter, but you can believe about 20 of them in this case. And it has a standard audio codec for stereo in and stereo out, so you can hook a microphone to it as well as hooking up your receiver. And it has a transmit port, so you can drive your transmitter and off you go. Up here is some early prototypes of evaluation of the various A to D converters before we settled on this one. And that particular picture is from a lab in Perth, Australia. Phil Harmon, BK6APH. Okay, well, Phil in Ohio is very interested in high-speed digitizing direct receiver, so he came up with this thing he called Mercury, and this is a prototype of it. You can see the Ozzy board down here, and then as just a little hack in order to tie in an evaluation board from Linear Technology, who makes the A to D converter. This again is from the lab in Perth, Australia, and there was a contest last weekend, I understand. Has anybody heard of a weekend was not a contest? Yes, there were. Okay, it's just been confirmed. In fact, there was a contest last weekend. Okay. And apparently it's quite a popular contest, and Phil was using this as his receiver, and he had some other pretty serious contest operators at his QTH, and all of them agreed that this was the best receiver that they had ever listened to and ever used during a contest. Really good performance, very wide dynamic range, all the rest of it. So this one is coming down the pipe, and we're pretty excited about it. Phil was taking a slightly different approach. This is the other Phil in Ohio. He's got a little project he calls QuickSilver. QuickSilver has the same A to D converter and the same FPGA, but it has the USB stuff on it. Basically, it's most of an Aussie board and a prototype of the Mercury board all tied into one card, so you don't need the backbone. It's just a single board, very interesting receiver. Don't know that it's available yet, and it's not necessarily part of the HPSDR stuff, but it might be, because it does have that catchy name, although QuickSilver isn't from mythology. It's close enough to Mercury that we let it go. Okay, there's another project that's going on right now that's called Penelope. This is using not an A to D converter, but a digital analog converter running at a couple hundred megahertz, 125, something like that. So it'll go from DC to 6 meters and generate whatever you want, sideband, FM, source scan, TD, fill in the blank. And all the heavy lifting is done in an FPGA, and it will hook up to the USB port through Ozzy. And the prototype, I said, measuring half a watt to 1 watt output. That's on the transmit side. We wanted to have enough power so that you could actually make a QSO with the thing, but rather than a transmitter, I call it an exciter right there. That one is coming along pretty well. Phil's done, the two Phils have done a lot of prototyping. I'm doing the circuit board layout for that one, and the circuit board layout is about maybe 40% complete now. So I'm hoping within the next 3 weeks to have that circuit board layout done, and we'll see where it goes. I think it was a bit of a play on words that Phil in Perth was calling Penelope a duck, digital up converter. I didn't know, I thought Howard was a more appropriate name for that. But he's stuck with Penelope. But anyway, that gives you an idea of what's going on. You've got the FPGA taking digital stuff and making numbers that correspond to RF, which comes out of this guy, goes through the standard filters and amplifiers, and off you go. And a way to hook up things to monitor ALC and whatnot, so you can be sure that you're not running less than 1.5 kilowatts. And there's also some spigots coming out of this guy. If they're shown here, they should be. Yeah, envelope out. There's also some stuff, we want to experiment with something called envelope elimination and restoration. What does that mean? That's basically a way to make a really high efficiency, high power linear amplifier that doesn't need a heat sink. ANSAT's been using this kind of technology for years. DJ4ZC, Carl Meinzer, was his PhD thesis on how to do this kind of stuff, where you can use a nonlinear amplifier for linear amplification. And nowadays, we can get some really high efficiency outputs. Well, back in the 70s, Carl did his prototype stuff. In those days in Germany, the rules didn't limit how much power you could run. They limited the plate dissipation, how much heat were you generating. And the rules there were on the order of a couple hundred watts of heat that you could generate, which for most things, if you're running sideband, it would be maybe 400 watts is about all you could do, because you only get about 50% DC to RF conversion. If you're running CW, maybe you could run, 600 or 700 watts output, something like that. Well, Carl's transmitters were running at about 95%. Well, if you run the numbers backwards, you'll understand that they could make a little desktop amplifier that 200 watts of heat for your basement in Germany in the wintertime, but you have about 5 kilowatts. And it was perfectly legal. The problem they had was the transmission lines, antennas, parking, some of these other issues. When I talked to Carl about this in Germany last January, it sounded like so much fun we had to put the hooks in for this. Okay, I'm a guy that thinks that if you're going to go out and operate on a picnic table, or if you're going to take your SOS machine on a hike with Bruce up along the Pacific Crest Trail, then you don't really want to have a PC plugged into it in order to operate the radio. Anybody ever been out, I was going to say on a sunny day, but this is in Northwest, Have any of you ever been outdoors on a relatively bright ambient light day and tried to read the screen on your laptop? You'll understand what I mean. So I'm a great believer in embedded digital signal processors. So Sasquatch, not from Germany, not from Greek, but still Sasquatch is a mythological character. At least that's what I was told when I lived in Arizona. The idea is that this is just a big bad dude that's going to do the heavy lifting for us with a digital signal processor that's running a few 100 billion instructions per second. And this particular thing that's showing a block diagram of it, you look at the top and you say L band AGC, U band AGC, what's that all about? Is this only for microwave? No, this is the core of something that we're doing with an ANSAC called the software-defined transponder, where we're using software-defined radio techniques in order to create what we hope will be the best transponder that you've never heard in an amateur satellite that will be going, we're hoping, up in the Phase 3E spacecraft that might be launched this year, certainly hopefully by next year, and the Eagle project from ANSAC. One of the things we have to do for that is radiation qualify the parts that we use, because we always use parts that NASA and everybody else says you can't use these in space. That's our first indicator that says we believe we can. We need to make the board small enough to go into a device that puts a lot of radiation on this part to see if the part's going to work. And of course, the way that you do that, where's your favorite local radiation source in those towns? Local hospital, right? So we do our radiation testing where people think we're putting in sacks of blood for the Red Cross, and in fact, it's pieces of hardware for ANSAC. So we don't worry when the alarms go off in the hospital that we just killed the patient. But. Okay, Horton. This was a mythology from Dr. Seuss. And it's the idea is to do something like we saw with QuickSilver, but in this case it's a quadrature sampling detector arrangement. Right now it's such a proposal. Gibraltar. One of the things that the microwave guys really want to do, and the moon bounce guys and other people, they want to synchronize all of the oscillators in their radios so that when they don't hear something, they don't believe it's their fault. So we've got one guy, Rick, who doesn't use GPS, gives you an idea what his interests are, and he makes his living by making really stable, really low noise oscillators. Rick is going to be basically opening the chest of the corporate jewels and giving us Gibraltar, which is going to be a very stable 10 megahertz reference that we can then plug into the Atlas backplane and tie all of these other boards to it, so we have really, really tight frequency and phase control. You want to do diversity deception. Maybe the reason you're not hearing that 9600 quad UHF digipeters because of multipass, so you put up 2 antennas, you play these kind of games, and suddenly you've got good coverage in front. This was pending the open hardware license, but that seems to be pretty well in hand now, so I think work is going to be coming forth here pretty soon. Then, of course, there's Proteus. You've got to have a prototype board. Since you have all the prototype stuff for software and things like Visual Studio that we saw earlier, you've got to have it for the hardware side as well, even for a software-defined radio. So the idea is that somebody wants to come up with a thing called Proteus to do prototyping. And again, the idea is it's just for you to have fun. Stick parts on here, make mistakes, short things together. Look, in the end, all the current goes to ground anyway, right? So it's a faster path. Okay, and then there's another board. This was the second board to come out of this project. You notice it's not in an anti-static pack. That's this one, also from mythology, a guy named Pinocchio. And the whole idea of this was you could plug it into the Atlas bus and then plug your real board on the other side of that. And then you could take your oscilloscope probe, and when you shorted something out and let the smoke out, you could see where the smoke was coming out. So that was one that I whipped up early on because it didn't have any software either. Ray is proposed a board called Phoenix, which is basically similar in function to the SDR 1000 was originally, which is a little 1 watt HF radio. And in this case, so you have your SDR 1000, the sound card, and the PC, and then you can take away the sound card and replace with the stuff I showed you, and you can replace the PC with the Sasquatch board that I showed you on the screen, and then you can replace the SDR 1000 with the Phoenix board, and now it's all inside your HPSDR Atlas bus. Odyssey, I think this one is really cool. This is putting a software-defined transponder Many of you, I suppose, last year heard about SUPSAT-1, where they took a spacesuit from the space station, they filled it full of garbage, they put a 2-meter transmitter on it, and they threw it out. And as it was drifting away, you can clearly hear, I can't do that, Hal. As opposed to A. Okay, so this is using a DSP from Microchip, which is a very low-end digital signal processor, but it's still enough. And the idea is to make a software-defined transponder. We have a software-defined receiver feeding a software-defined transmitter, all on board this little thing running on batteries. And you'll be able to talk through this space station so we can repeat your APRS packets. Maybe it has GPS on it, it can tell you where it is, so it won't really be lost in space. So that's the first application. They decided to call it Odyssey. And I wasn't sure when Homer wrote the Odyssey, that's what he really had in mind. Anyway, get serious now. Okay, HPSDR, where do you get these modules? Well, the designs, as I say, are open source. If you go to the HPSDR website, you go look on the wiki, you follow the different pages to Janus or whatever, you'll find links to the circuit board layout files, the Gerber files, that you can then download and submit to your favorite circuit board house. You'll find the software, you'll find how to get to the software. All the information you need, parts lists, all the rest of it. So if you want to get a board today, you can get a board today, you can build it, you can go for it. It's a little expensive to do it one by one that way, but you can. So what TAPR has done has organized, effectively it's a group buy. It's a group buy, you don't have to offer a one, so it's a group buy. And what they're doing is getting people that are interested in getting some of these boards to order them, and then they will go ahead and get them fabricated and get them shipped back to you as assembled and tested boards. Now that's for the Ozy board and the Janus board. Those will be assembled and tested. And the order window for that is now. They're going to make one run of these things, and then if the residual interest happens after that, they'll make another run. Depending upon the size of the spectrum, the price may be higher or lower if they get what I had to say. It just depends upon the order size. The initial order size is going to be of about 600 units. The Atlas backplane is available as a kit. You can just order that one up yourself. And if you don't want to, then you talk your friend into it. You grab the paint, you grab the whitewash in the fence, and you get your friends, and they'll build it for you. Pinocchio the same way. It's a kit. And then Mercury and Penelope, I expect to be following as the next ones, and we'll see what happens after that. Gibraltar, I hope soon. So to sort of close the formal part of the presentation here, I just want to say that this HPSDR thing is really, you get the modules and you make your radio. You configure the hardware modules. I'd rather use a quadrature sampling detector, whatever that is. You notice I haven't told you what that is, so you can ask the question. Or a quadrature sampling exciter-based thing. Maybe you like the direct digital conversion stuff like Mercury and Penelope. You can configure it the way you want. Maybe you just want something to control your SDR 1000. Maybe you want something to control your little software $40 transceiver, whatever. The idea is that it's modules, building blocks. It's Lego for hands. Anybody can participate, but I think even more important, anyone can learn. The information is there, it's free. And it's international participation. The manuals, for example, if you look at some of the manuals, you see a name Horst and a DL6, I think, prefix. All over in Germany has written the manuals for assembling the first boards. Whereas there's been cooperation between Australia and Europe and North America in order to produce the designs. TAPR has stepped in and funded some of the prototypes. AMSAT has stepped up to the plate. And they've not only helped TAPR a little bit financially to get this thing launched, but they were able to acquire about $1 million worth of development software. This is really high-end circuit board design tools and really high-end FPGA tools and all the rest of it. And they're making that available to the HPSDR developer community. So if you can come up with a name for mythology, come up with an idea, and you're willing to do some work, then you can get yourself plugged into some of these tools, and you don't have to worry about where am I going to get the money to buy a $10,000 circuit board layout package. You can use ANSATs. They've got a floating license, and you can be one of the users. So to me, it's really great to see this level of cooperation with different high-tech organizations, ANSAT, TAPR, grassroots support, international. It's what ham radio is all about. It's learning, it's having fun, it's experimenting, and it's pushing a little bit, maybe not the state of the art for people that have gigantic multi-billion-dollar budgets, but it's pushing the state of the art certainly with amateur radio. It's coming from the amateur community, and it's a spontaneous thing. For me, when I was involved with TAPR and TAPR radio in 1981, 82, 83, when that stuff was being launched, it was really exciting times. And I haven't had that level of enthusiasm and excitement in amateur radio until this HPSDR thing started. And I just found it to be, it's a lot of fun for me, and so please excuse me if I'm having a lot of fun, but come join the fun. So I want to thank you for your attention, and I'm here to try to obfuscate some answers to questions. Yes, sir.
I thought about 16-bit DSP, what about 32-bit? The second question is, Icon, SDR, how do you tell about both compared with
Okay, let me answer the first question first, if I can remember it. I talked about 16-bit DSP, what about 32? The Sasquatch board that I mentioned is a 32-bit floating point DSP engine that runs, it has multiple execution units running in parallel, so it runs about 1.4 billion, 1.2 billion floating point operations per second. Now the second question was about an Icon radio?
Yeah, Icon needs an SDR. They sell commercial.
I'm not familiar with an Icon SDR. I'm sorry. Bruce?
The simplest radio that I own is a VLF receiver. Basically, it receives the RF equivalent of the audio range. And because a certain frequency, 60 hertz, is within that audio range, this radio is totally useless in any urban area. You take it up in the mountains, you can hear lots of wonderful stuff. Now, thinking about that problem, can you think of an approach, a software-defined radio approach, where you could do VLF right into this little power grid?
Yes. Let me elaborate on that. Yeah. All you got to do is knock out the power grid, Bruce. However, if you don't want to attract homeland security people, the trick to that is to have enough dynamic range in the receiver. It's just like the two-tone testing. And if you look at any QSC reports on receivers, they talk about blocking dynamic range and IMD3 and all that sort of stuff. If the noise of your 60 hertz amplitude doesn't exceed the dynamic range of your A to D converter, you can then, in software, notch out all that 60 hertz stuff and listen to the frequencies of interest. And you can put notches that are, that are, for practical purposes, infinitely deep, that exceed the dynamic, that exceed the range of the transducers. So you can, as long as it's not overloaded. Now, of course, you've got 60 hertz, 120 hertz, 180 hertz, etc. You can just drop notches on all of those. If the insect or the bat or whatever you're listening to has a sore throat that day and is down around 60 hertz, you're not going to hear it because it'll be in the notch. But otherwise, yeah, you can listen to the signals of nature of those frequencies. What?
On the 60 hertz thing, in the medical industry, one of the ways we got rid of 60 hertz when you're trying to do ECGs, microvolt signals, was to build a copy of what the 60 hertz signal was and then invert it and subtract it, and it kept you having to design an impossible filter. And the 60 hertz frequency actually moves around quite a bit on a short-term basis, so a really sharp fixed frequency notch would not be that useful, and that's why. Anyway, the real question I have is, where in the architecture do you think you could cut such that the hardware part of it could be separated over a broadband link to a remote back-end anywhere else in the world?
Okay, and the answer to that is it's coming soon. One of Phil Covington's big pushes is for the next generation of Ozzy. He wants to be 1 gigabit Ethernet interface rather than the USB 2.0 interface. So currently, what you could do is have a USB plugged into a computer or some server that's tied into the network, and then broadband your way back to that. But the intent is to have a version of Aussie that is directly gigabit Ethernet, and not just gigabit Ethernet capable, but capable of punching a lot of stuff using that bandwidth. Unlike some of the USB 2.0 compatible things you see that have a hard time getting 10,000 bits per second. Yeah, that's very much on a lot of people's thoughts. Also, the software and the SDR 1000, their software thing right now is called Power SDR. It's going to a generation 2 where the user interface is being separated from the radio control interface, being separated from the digital signal processing interface. So you'll be able to then easily break those over separate computers over any kind of LAN or any kind of a network that has a bandwidth to allow that communication between those modules. And the people that are dealing with this stuff in the Linux world are currently already doing that sort of thing. Yes? I'm sorry?
They were hooking into, or they were receiving the Mars reconnaissance orbiter signals, and in that, my question is, Gibraltar is supposed to be the stable clock. There's a completely different version of what stable clock means to those guys as opposed to what I'm wondering how stable Gibraltar will be in comparison, because that's kind of some stuff I would kind of be interested in, is that and the microwave down converters. Anyway, can you shed some light on that?
Yeah, okay. I'll just kind of move through here, but I'm not going to get past the hat. I'm not looking for money. Okay. The stuff that was done by the ANSAT DL guys who got access to a decommissioned radio telescope and then started getting signals from Mars Global Surveyor, and I believe that they've also talked to Voyager. And they were using it recently at the time that Venus was near enough to the Earth. They were attempting Venus bounce, and they didn't quite succeed, but they were within about 0.2 dB of succeeding at that. For those kinds of clocks, Gibraltar provides the stability you need. We're talking about things that are stabilities in the, there's all kinds of stability. There's a short-term stability, there's noise on the signal, there's phase noise, there's all these things. But if you use the right ionized oscillator that Rick has identified, and you use this technology to tie it up, you're going to be, parts in 10 to the 11, parts in 10 to the 12 kind of stabilities. It's absolutely state-of-the-art. Rick's company sells the really highly stable oscillators to the three-letter agencies, and that's how he manages to support his lifestyle. We'll be having access to that kind of stability literally. In terms of the down converters, the trick there is that you have to make a low enough noise local oscillator and then slate it to this 10 megahertz reference. So Gibraltar won't provide that high frequency, but it will provide the reference that you can use to create such a microwave LO. There's also a group called Microwave SDR. I'm not sure if it's mwsdr.de or something. I believe it's located in Germany. But these are amateurs that are microwave experimental guys that are using SDR for microwave. I think that they're mostly using SDR 1000s for their IFs at this point. Another website that you might want to go to is Leafs, which is the Linrad website. He's very much into this, into some very interesting things, including the kind of noise reduction that Ward was talking about. Some very advanced and sophisticated stuff where you put predictive things inside of it and you subtract it out so you wind up with no distortion. Lots of, I expect development in those areas to be happening in the very near future. That is to say within my lifetime. Yes.
There was a fellow locally, Ray Pettit, that used to do some very fancy stuff with it, like that's wide communication, hitting a high stability oscillator. These guys doing the Venus bounce, were they attempting to do a bandwidth of a hertz wide in terms of the zero crossing detectors and so forth that are available? So people doing any development along those lines that Pettit had put forth some 10 or 15 years ago?
Yeah, that's related to the coherent CW, the CCW work that he did, and then later he went on to HAL and developed their HF, fairly fast HF stuff. I'm not sure what the detailed techniques were that they were attempting to use for the Venus bounce. I know the guys that were doing it, and these guys are people that are incredibly brilliant. But I don't know enough of the detail. I wouldn't want to pretend that I do not know. In the back?
Yeah, I don't even know if this is a good question. But when you're talking about things like tremendous dynamic ranges and that kind of thing, when is this kind of stuff going to be really available to the radar from, say, Pentec or Odyssey or Kenwood radio manufacturers?
Okay.
And how much might it cost?
Okay, well, if Kenwood or ICOM or Yaesu makes it, I'm sure it will cost a lot. FGDX 9000, IC 7800, I don't know where Kenwood is in that list.
But is this mostly software development, one-time development, it works?
Well, in any of these things, for example, the software that's currently running inside of most radios that you can get is capable of extreme dynamic range. It's the ADD converters, it's the hardware that's limiting it. The best direct digital unit that I know that's available in the amateur community today is the SDR 14, the slide that I showed a little earlier. That's only using a 14-bit ADD running at 65 megahertz. The Mercury board is going to be a 16-bit ADD that has a lot of tricks to make every one of those bits meaningful and running at 130 megahertz. So we'll get, another 12 to 20 dB of dynamic range over the SDR 14. What's going to happen after that? It depends upon the market that's driving the people that are making these parts. One of the reasons that the 14-bit parts became very popular was because if you're doing a cell phone site with multiple carriers, 14 bits, as it turns out, between 12 and 14 is a magic number in order to make the cell phone system work reliably, and they don't care about it any more than that. So it's been hard to get some of these components, and we don't have enough volume to drive that sort of thing. So in the end, it comes down to those kinds of issues. Yes?
Yes, what I see here is the ability to pull out multiple signals simultaneously from the same antenna source. So is there any research being done where you could have one killer antenna site tap into it through an Ethernet connection and multiple hands could use that receiver site with the software-defined radio?
It's an interesting application, and I don't know of any particular research that's going on specifically for that application, but I do know that there are people that are planning on putting these receivers up and then having them on the web, and because they are capable of multiple channels, you can have multiple people using it at the same time. There are certain limitations to that. For example, the Mercury board will be able to provide two independently tunable outputs, so you can look at 20 meters and 40 meters at the same time, for example. After that, if you have a sufficiently fat pipe to get that stuff to you, you can then run the rest of the software that then selects the specific signal that you want and tune on down from there. There's also, because with Gibraltar, keep getting the raspberry from that speaker. With Gibraltar, you'll be able to synchronize multiple of these things, so you can do diversity reception. So you could have multiple receivers at multiple sites being used by multiple people, and it goes on and on from there. You get 10 antennas, and you put them in the right places, and you basically have beam streaming. And so you can have you could be listening to a signal over there, and I could be listening to a signal at a different frequency or the same frequency over there at the same time, and we're getting directional affection. In fact, that's the kind of technique we're going to be using on the Eagle spacecraft. So when we have a spinning spacecraft that's moving around, if this is the Earth, the spacecraft is pointed here and moving around, we're going to be able to steer that beam electrically because we have enough antennas that we're actually running a thing called a fast Fourier transform over that beam pattern so that we can cause the signal to go where we can attempt to cause the signal to go where we believe the Earth is. And I think we're going to use C# for that because we use that statement that says try. Okay. How's that? Ooh, Pic A Star. Any other questions? Sir. Yes, that was the one that I showed earlier, the Sasquatch series, from Tony Parks. Yeah, it's a Yahoo group, I think, but Yahoo, Google, whatever, you can Google it and find it. But yeah, they're little $20 receivers, and they're very interesting for what they are. Now, they're not going to give you the incredible dynamic range and all the rest of it that the technology is capable of, but for $20, it'll run circles around most things you can buy for, up to 50 times that price, up to $1,000. I think that receiver on the band that it's on is probably as good as most, general purpose commercial amateur receivers, although not the high end. At $20, you just have to convince your wife why it was more important than buying those roses. Yes. Yeah, the question is more details on the cerebral antenna stuff. And I'm like the one fellow said he wasn't sure it was a good question. I know that I don't know enough to give you a good answer. Sorry. I think that's it. Thank you very much.